It's 1913. The sun is out, the roof is down, and you are running out of gas. But luckily, there's a brand new convenience right around the corner. You pull in and fill up your car in seconds. You are sitting behind the wheel of a brand new Ford Model T. Paying an attendant to dispense fuel at a dedicated street corner was an entirely novel concept, and it laid the foundation for modern transit. This map shows the rapid expansion of that single idea. The car market multiplied, and soon over 150,000 stations dotted the country. Today, that global network pumps out 3 billion gallons of fuel every single day. But the ultra-efficient pit stops we take for granted today were born out of a deeply chaotic, highly dangerous early necessity. Before cars filled the streets, kerosene was largely a household utility. People relied on it primarily to keep their stoves burning and their lamps lit after dark. When a family ran low, they walked to the local hardware store to buy more. Inside, an employee would haul out a drum of raw kerosene and pour it directly into whatever tin or can the customer brought from home. Once early automobiles hit the market, this exact same process carried over. A driver would haul their hardware store tin out to the vehicle and try to pour the liquid into the gas tank using a simple funnel. It was a slow procedure, highly prone to spilling flammable liquid. As vehicle numbers climbed, hauling tins from general stores became a severe logistical bottleneck. An American inventor named Sylvanus Bowser recognized the problem and developed the first dedicated mechanical solution. As this diagram demonstrates, he built a hand-driven mechanism that squeezed kerosene from a container, pushed it through a one-way valve, and out of a nozzle. One full crank of the handle dispensed exactly 1 gallon of fuel. These new pumps began appearing on city curbs. Instead of buying a tin from a hardware clerk, drivers could pull up to the street side and let an attendant pump it straight in. But the closed metal housing created a problem of trust. Customers paid per gallon, yet couldn't see the liquid moving through the opaque pipes to confirm the correct volume. The visible fuel pump solved this consumer anxiety by putting the transaction out in the open. The attendant pumped fuel into a transparent, numbered glass tank, measuring the exact amount. Once confirmed, gravity drained that precise volume into the car. Being able to visually verify the purchase secured trust, but the small physical scale of these early curbside pumps was completely unprepared for the mathematical crisis approaching. In 1900, there were roughly 8,000 cars driving in the entire United States. This chart shows the massive adoption curve over the following decade. Just 12 years later, total car ownership spiked to 1.2 million vehicles. City avenues that were historically empty suddenly filled with machines. Cars stacked up bumper to bumper in dense traffic jams. With thousands of cars competing for fuel on the same blocks, the curbside infrastructure failed. Long lines formed around every single pump, and their 50-gallon tanks routinely ran dry. Worse, maintaining dozens of these small, above-ground tanks scattered along sidewalks meant large volumes of highly flammable liquid were constantly exposed to the friction and collisions of heavy urban traffic. Expanding fuel reserves above ground was dangerous. To keep cities from either running out of gas or catching fire, the storage architecture needed an immediate overhaul. In 1913, the Gulf Oil Company executed that redesign by opening the first dedicated fueling station in Pittsburgh. Instead of small barrels on the sidewalk, they buried a massive, high-capacity storage tank safely beneath the street. From that single underground reserve, pipes ran upward to 6 surface pumps. Now, half a dozen cars could fill up simultaneously. On its first day, the station sold just 30 gallons, but word spread. By the end of the week, daily sales had climbed to 350 gallons. At roughly 27 cents per gallon, the economics of the centralized operation were proven. By hiding the dangerous bulk storage below the surface, while vastly expanding the number of pumps above, Gulf Oil established a commercially viable, high-volume model. Similar purpose-built brick-and-mortar stations, complete with protective canopies and multi-pump lanes, rapidly spread across the country. With a sprawling infrastructure network now dotting the map, drivers were officially untethered from their local hardware store. Widespread long-distance travel became a reality, but the kerosene that had powered this initial boom was already being phased out in favor of a different liquid. Gasoline burned significantly hotter and ran much cleaner inside the newly refined combustion engines. However, that efficiency came with extreme volatility. Gasoline vaporized quickly at room temperature, turning the smallest spark into a lethal threat. The underground storage tanks had solved the capacity crisis of the kerosene era, but filling those exact same tanks with gasoline would soon test whether these new stations were a modern convenience or a bomb waiting to go off. By the 1920s, drivers were abandoning kerosene for gasoline. It burned more easily and ran engines more efficiently, but this introduced a severe chemical hazard. The issue is a substance's flashpoint. Kerosene sits completely stable until 38 degrees Celsius, only then releasing flammable vapor. Gasoline, however, has a flashpoint of minus 40 degrees. At room temperature, it continuously releases explosive gas. Because gasoline constantly leaked this vapor, pulling up to a pump meant entering an explosive zone. Refueling a car was dangerous enough that it strictly required a trained attendant to handle the hose and manage the risk. The earliest gas stations were essentially hazardous material transfer sites. The entire operation was bottlenecked by the need for specialized human caution at every single pump. That changed in 1947 when Frank Ulrich decided to cut costs. He opened a gas station, fired the attendants, and let the public pump their own fuel. Removing the employee overhead allowed him to drop his prices from 23 cents a gallon down to 18 cents. Drivers flocked to the station, buying 500,000 gallons in the very first month. But everyday drivers lacked the training to safely handle the pumps. Without knowing when their tanks were completely full, untrained customers routinely overfilled their cars, spilling raw gasoline across the pavement. Those persistent spills prompted lawmakers across the country to ban self-serve stations entirely. Ulrich proved that cheap, self-serve fuel was highly profitable, but for the model to survive legally, engineers had to figure out how to automate the safety measures that the untrained public lacked. The first line of defense against overflowing tanks was a simple mechanical float installed directly inside the nozzle. As the liquid level in the car rose, the float pushed upward, cutting off the flow of fuel. At the pump itself, early stations utilized mechanical flow meters. As gasoline pushed through the lines, it turned physical gears. The pump acted as a localized analog computer, spinning the exact monetary cost based on the volume of fuel delivered. To adjust the price per gallon, an operator had to unlock the pump face and manipulate a 3-pin device. Changing the gear ratios by hand altered the fuel flow multiplier for the next customer. These mechanical upgrades solved the immediate surface problems of billing and basic overfilling, but they entirely ignored a far deadlier threat buried deep beneath the station. Millions of gallons of gasoline were sitting in giant steel tanks under the ground. Over time, that steel corroded. It began leaking raw fuel directly into the surrounding soil, while thick layers of explosive gas built up inside the empty space of the tank. Whenever a delivery truck arrived to refill those storage tanks, the incoming liquid physically pushed those massive vapor clouds straight out into the open atmosphere. To secure the storage, engineers completely redesigned the underground tank using modern fiberglass. Today, when a truck arrives, it connects directly to a secure surface valve. This diagram reveals the first major safeguard inside that fiberglass tank. As the liquid level rises during a delivery, a mechanical flapper valve physically flips up the exact moment the tank hits 95% capacity, preventing the truck from overfilling it. At the same time, the system captures the vapor. A secondary valve collects the displaced gas as the liquid pours in, channeling it back up through a separate hose directly into the delivery truck, where it is driven back to a processing plant and recycled into usable fuel. By sealing the entire delivery cycle, modern underground systems turned a toxic, highly combustible storage pit into a perfect zero-waste loop. When a driver pulls up to the surface, a pump sitting at the very bottom of that underground tank kicks on, pushing the fuel up through a series of filters and into the dispenser. The fuel then reaches the modern nozzle. Rather than a rudimentary open and close valve, this handheld device is an intricate mechanical sensor that actively determines when your car is full. This animated cross-section shows exactly how it works. As gasoline is forced through a narrow restriction inside the nozzle, its velocity increases. This creates a distinct low-pressure region, known as the Venturi effect. That low-pressure zone acts like a vacuum. It constantly sucks outside air in through a tiny secondary hole located at the very tip of the nozzle, mixing that air with the flowing fuel. Higher up inside the handle sits the main safety mechanism, a small sealed compartment containing a flexible membrane. Below it, the main valve lever is held securely open by a set of tiny steel ball bearings. The moment the rising gasoline inside your car covers the tip of the nozzle, it blocks that tiny air hole. The suction instantly stops, creating a sudden, powerful vacuum inside the secondary tube that forcefully pulls the flexible membrane upward. When that membrane lifts, the ball bearings holding the main lever drop out of their sockets. Without their support, the lever collapses, and a heavy metal spring slams the main valve shut. In a fraction of a second. After the 1970s, automobile engines became much more efficient. Cars required fewer trips to fill up, and the physical footprint of the gas station slowly began to recede across the country. Yet every time you squeeze that handle, you are relying on over a century of relentless engineering. Designers took one of the most volatile liquids on Earth and controlled it so perfectly that handling it is completely safe and entirely invisible, and beautifully mundane.